Okay, welcome to the video key for the acid-base take-home test. We are going to take a look at a couple of these together. Okay. First thing, I'm going to offer you some extra credit for watching. Okay. Right here, I want you to write big blue bitter base. Okay. So those are my buzz. Big blue bitter base. That's how I remember the properties of bases. Okay, so that should help you fill out this side on your own for bases. For acids, acids like a lemon tends to be sour. I'm going to use blue for this. Acids are sour. Both acids and bases are electrolytes, which means they conduct electricity in solution. Acids react with metals to produce hydrogen gas. Acids are kind of all about hydrogen, and bases are all about hydroxide, OH. Acids release the hydrogen ion, H+, when dissolved in water. Acids have a pH 0 to 6, or really 0 to 7. 7 is technically neutral, but anything under 7 is acidic. Okay, big, bitter blue base. Okay, so bases will always look blue on litmus paper. Acids will always look red. So acids will turn blue litmus paper to red, and they will keep red litmus paper red. So at the end, acids are always going to end up red on litmus paper. Okay, so using that knowledge, you can finish this side. Okay, the symbol for the hydrogen ion and hydroxide ion. And then the erroneous definition of acids and bases is the definition we've been using in class all unit, okay? And that's that acids start with an H and release the H+ ion when you put it in water, in solution. Bases are always going to end in OH and will release the OH ion in water, okay? Bronsted-Lowry is a more complete definition of acids and bases, and you needed to memorize what Bronsted-Lowry thinks about acids and bases. So I just kind of put this there. The P is kind of hiding in the B for Bronsted-Lowry. Okay, Bronsted-Lowry is all about protons. Okay, so for both, it's a proton something. Okay, releasing or producing, giving away is the same thing as donating. So donor. Okay, acids release H+. H+ and protons are the same thing. It's different names for the same thing. So proton donor. Okay, that's what acids are. And then bases are the opposite. So proton acceptor. Okay, make sure you're making flashcards. You need to recognize these types of acids and bases. You need to know the definition for Bronsted and Lowry. Alright, stuff in blue is stuff you need to complete on your own. But I want to look at 6, 7, and 8 with you, okay? So it says, which of the following would not form an electrolyte solution? So I'm going to circle the word not. Okay, which of the following would not be an electrolyte? Because in class we learned 3 types of compounds are electrolytic. Acids, bases, and salt. So the thing that is not an electrolyte would be covalent. Okay, so HCl is an acid, which means it is an electrolyte. NaCl, that's a metal, non-metal. That means it's an ionic salt. OH means this is a base. PO4. Phosphorus and oxygen are both non-metals, which means it's on this side of the periodic table. C for covalent. So this one would not be an electrolyte. Neutralization reactions. If you neutralize a threat, you're removing the threat. So to neutralize means to make safe. And that's what happens when you mix an acid with a base. Okay. If you mix a pH 7 and a pH 14, it'll meet in the middle. Excuse me, if you mix a 0 and a 14, okay, they'll meet in the middle and be pH 7, which is safe. The products of neutralization reactions. So if you're mixing an H plus and an OH minus, that's two H's and an O. So that's water. H2O, which is the same thing as HOH. Okay. So one of your products is always water. The other thing would be ionic salts. Okay. So neutralization reactions, acid plus a base makes water and salt. Okay. Looking at the bottom part of this page. Okay. Strong bases. Strong acids and strong bases are rare, but that means that 100% of it will dissolve or dissociate. So strong means it will partially, I did that wrong, will completely, strong means completely dissociate, making a lot of base ions, which is OH. So if there are a lot of charged things, it means it's a strong electrical conductor. Geez, there we go, electrolyte. Okay. A solution A has a pH of 2. When you mix it with solution B, the new combined pH is 9. So I'm going to go from 2 to 9. Solution B must have been acidic or basic, adding this or this to the solution. So I put this down here. 0 to 7 to 14. Big, bitter, blue base. Okay? Big on the pH scale is a base. Low on the pH scale is acid. So I was at a pH of 2, and now I am at a pH of 9, which means I got more basic. Okay? If I had added acid to this, it wouldn't have gotten closer to being a base. So I would say this must have been basic, and when you're basic, you add the base ion. Okay. All right. Go ahead and turn to page 2. We'll take a look at some of our naming on page 2. All right. So acids, again, the Arrhenius definition of acid means we can recognize it because an acid is always going to start with H and then something else, and bases will always end with OH. So that's how I was able to go through and do acid and base. If it's neither of those, right, like this one starts with potassium and ends with PO4, which is phosphates, so it's neither, that means it's ionic salt. So I put an S for salt. We're going to do these yellow ones together. The blue ones I'm leaving for you to do on your own. Okay, so H3P, I know that's an acid because it starts with an H, so I'm going to think back to my acid naming rules, which are this. Acids begin with H, and then I have to decide, are there 2 elements in it or 3 or more elements? So I know which rules to use. So that's just hydrogen and phosphorus, which means we're going to use these rules. I'm going to say hydro something ic acid. So if it's phosphorus, I'd say hydrophosphic acid. All right, hydro. Okay, and then phosphorus and sulfur have extra weird letters, so it's actually hydrophosphoric acid. Okay, that's all right if you forgot those letters. But I do say hydro this time because there are only 2 capital letters. F is also an acid because it starts with H, but I see 1, 2, 3 capital letters plus another H. So that means we have a hidden polyatomic ion. So I'm going to put the parentheses back, and on this one too. Okay, while you do that one on your own. So this one's still an acid, but I don't have 2 elements. So I use these rules. It's an oxyacid. There's a polyatomic ion in it, no hydro prefix. So I just start with the polyatomic ion. So C2H3O2 is acetate. So I'd say acetate acid. But I do this. I ate too much. I feel icky now. So instead of acetate, I'd say acetic. Okay, instead of acetate, it's acetic acid. Like that. So you'll notice this one starts with hydro because there's no oxygen in it. This one has oxygen in it, so I cannot say hydro. All right. looking down at the rest of this, okay, I'm giving you the names and you're writing the formulas then. So silver nitrate is not acid. It doesn't say acid, and it doesn't say hydroxide. So I know it's not an acid or a base. That's just regular 4-step formulas. Okay. So we've been doing that one since October, Unit 3, when we learned that. Silver, the symbol is Ag, and then nitrate, the symbol is NO3. So I'd say Ag and NO3. Symbols, then charges. Silver is the 1 in the 1B exception block. That's always a +1. Nitrate, that says right here, is -1. So +1, -1, crisscross, reduce and erase. So AgNO3, like that, silver nitrate. I really like these next three. Sulfurous, sulfuric, and hydrosulfuric, okay? Because they look very similar, but they have 3 different formulas, so it helps us figure that out. So because they end with acid, if the name ends with acid, the formula starts with hydrogen. So all 3 of these start with hydrogen, even though this one is the only one that says hydro, okay? And hydrogen makes +1 charges. The tricky part of writing formulas is finding the second symbol. So sulfurous acid, the second symbol, we're going to use this idea. If the name has hydro in it, then the second symbol comes from the periodic table. This one does not have hydro in the name. It's just sulfurous. So I'm not allowed to use any of these. I would use one of the polyatomic ions. Okay? Sulfurous isn't on here. So our trick was bites are delish us. Okay? We changed the ite to the us. Now we need to turn it back. So that means it was sulfite as the second symbol. SO3 with a -2 charge. Sulfurous acid, okay, used to be ite. So that symbol, SO3 -2. Okay? So symbols, charges, crisscross, reduce and erase. Let me switch colors. H2, SO3, like that. And technically, because there's not a number in the parentheses, you can leave those parentheses off. I'm not going to, but you can. Okay, sulfuric acid. That's not sulfur. Okay? Because sulfur would be hydrosulfuric acid. Regular sulfuric acid is sulfate. Because I said sulfate, I ate too much. I feel icky now. So that means for this problem, my second symbol is SO4 with a -2 charge. So I'd say SO4 with a -2 charge, crisscross, H2SO4, like that. Okay, so sulfurous, sulfuric was like that. Okay, now this one says hydro. Hydro means it's from the periodic table, so this one is just sulfur. Okay. The second symbol, if the name is hydro, is something from the periodic table, so that's sulfur, or a big glare. Okay, so sulfur makes a -2 charge, go like that. H2S. Okay, go back and look at some of the homework videos if you're still struggling on naming and formula writing, or come in for tutorials, because that's a good chunk of your test. Alright. Looking down here, we're going to have some extra credit. Okay, what I want you to put is going to be for number 13 right here. Okay, number 13 says if there's an equal concentration of H plus and OH minus, the solution is most likely to have which pH? So the extra credit is H plus OH minus equals water, H2O. Okay, so if you put that right there and put 2 points extra credit, your teacher will give you the extra credit for that. Because if I mix equal amounts of acid and base, they form water, which means it's neutral, it's safe. So that would be pH of 7. Okay. 14 says if there are slightly less H plus than OH in a solution, what is it most likely to be? So that means I have a little bit less H plus and a little bit more OH minus, which means I have a little bit more of the base ion. So I wouldn't be acidic. I'm not going to be pH 6. Definitely not going to be pH 1. I'm not equal, so I won't be pH 7. I will be slightly basic, pH 8. If there are significantly more H plus than OH minus, so I'm going to say for this one, if there is a lot more H plus compared to OH minus, like that, then what would my pH be? It's going to be acidic, so not pH 8. This one is acidic, okay? This one's also acidic. This one's neutral. So it says significantly more. That means I'm not going to be a little bit acidic. I'm going to be very acidic, close to 0. That one. All right, looking at the rest of this page. Okay, you can check your answer on 16 and 21. But I wanted to look at this. So I'm using the pH to decide if it's an acid or a base. pH under 7 is acidic. So for this one, 6.6 milk is just a teeny tiny bit acidic. Not very acidic, a teeny tiny bit. And apples with a pH of 3.2 would be a lot more acidic. Okay. So acids, we said big bitter blue base. So bases are going to be blue. If this is an acid, then it would turn red. Okay. This one is also an acid, so acids will always end up red. Okay. Seawater was my only base, which is why it's the only one that will be blue. All right, pause it if you need more time on this page. Otherwise, let's go ahead and look at page 3. All right. So for page 3, this is a concept that students struggle with sometimes. It says a solution is becoming more acidic. So does that mean it's a lower pH or you're raising the pH? Okay. So if you're more acidic, we said big, bitter, blue base. So the bigger the pH is, okay, the lower the pH, the more acidic it is. So if you're becoming more acidic, if you're moving this way, your pH is a smaller number. That means you are lowering it. Okay? If you start at neutral and you're more acidic, you lower it. And that means you have more of which ion? If you're more acidic, it's always the H plus ion, the hydrogen acid ion. Okay? If a solution has its pH increased, it's becoming more. Okay? Increased means bigger. So if your pH is increasing, that means you're moving this direction. You're getting more basic. Okay, 24 is a huge skill. You're probably very frustrated with naming and formula writing if you don't know how to do number 24. It says to circle the acids that have hydro in their name. They all start with H, so all of their names end with acid. They don't all start with hydro. Okay, so a reminder, the rules for this, you only say hydro if there are 2 elements, if it's a binary acid. If there are more than 3 elements in your acid, then you cannot say hydro. So that's what I look at here. This is just hydrogen and bromine. So that one would be an acid. That would have hydro in the name, hydrobromic acid. This one has 1, 2, 3 capital letters, right? That's hydrogen with sulfite. So that would be sulfurous acid or sulfurous acid. Okay? It has 1 letters. H and I, only 2 elements. I would say hydroiodic acid. Okay? HClO3. ClO3 is chlorate. So I would call this chloric acid, but not hydro. Okay, 1, 2, 3, 4 capital letters, which means no hydro. Only 2 capital letters, that's binary, so hydrofluoric acid. So they're all acids, but only those 3 would have hydro in their names. Looking at number 25, this is Roman numeral review. Okay, so the first thing I want to do is go back and put in parentheses. Okay, there's not parentheses around these OHs, but they're all hydroxides. So circle the bases that are going to have Roman numerals in their names. I'm going to see if I can get all of this on the screen at once. Look at that. Okay, so aluminum right here, lithium, iron, sodium, whoa, and they're repelling each other. I didn't pick the right things for this. Strontium and cobalt. And that's not going to work either. Well, we'll do this then. How about I just write on it? Cobalt, iron, lithium, sodium, aluminum. Okay? So we've got a couple of things. My first 2 groups in the A families, 1A always makes a 1 charge, A for always. 2A family always makes a 2 charge. So these families never get Roman numerals. Okay, they don't need them, because the only kind of lithium is lithium 1. So I would not call this lithium 1 hydroxide, just lithium hydroxide. For sodium, just sodium hydroxide. Doesn't get a Roman numeral. Okay. Over here in that stair step, that's the exception block. The 1 and 1B that always makes a +1. The 2 and 2B that always make a +2. And the 3 and 3A that always make a +3. So the only kind of aluminum is aluminum 3. So I do not use a Roman numeral, just aluminum hydroxide. Iron and cobalt here in the B groups, okay? Anywhere that's not in the first 2 families or in the exception block. All of those other metals that are not in blue have to have Roman numerals, which means iron will and cobalt will, and I missed strontium down there. Strontium would not. So I would have to call this iron 3 hydroxide and cobalt 2 hydroxide. Roman numerals. Okay. All right, neutralization reactions. I want to show you some extra credit. I'm going to have you write this. Neutralization. Okay, a neutralization reaction is always an acid plus a base yields salt plus water. Okay. They tend to look very similar to double replacement reactions. It is a double replacement reaction, but it's a special one that gets its own name. Okay. So an acid plus a base. So that's what I'm looking for. Magnesium plus HCl. That's an acid, but magnesium is not a base. Okay. This would be a single replacement reaction, not neutralization. HF is an acid. LiOH is a base, and that's ionic salt and water, so that looks good. I am not going to pick it because I take out my garbage. I want to make sure the other ones aren't it. Okay. Just sodium plus chlorine. Okay, so there's no acid and no base. That's not it. That's a synthesis reaction. CH4 methane plus oxygen makes carbon dioxide and water. That is a combustion reaction. No acids and no bases there, so that one goes away, which means I feel comfortable saying this one is the only neutralization because it's an acid plus a base makes salts and water. All right, let's take a look at some more on this page. You can check your answers on the top and the bottom here. Okay, so I corrected this. When mixing acid and water, you always add acid to the water, and you do that slowly while stirring, wearing a lab coat, and washing your hands, not quickly. Okay. The H plus ion, which is a proton, is always released by acids, and phenolphthalein turns that bright, hot pink color that we saw in lab when it's basic, 8.3, so that's a base. Okay. All right. So let's look at page 4. Let Let me get all my stuff ready for you. Okay, so the matching at the top of this page, those are some real important vocab words. Okay, I want to look at the blue ones with you. So oxidation and reduction. We learned the trick oil rig, O-I-L-R-I-G, which means oxidation is losing electrons, reduction is gaining electrons. So for reduction, we're going to want to find this one. It says when you lose electrons, occurs when a neutral atom loses electrons. That's not reduction, that's not gaining, that would be losing. So I could say oxidation is losing electrons. C. O-I-L. Okay? And then we want to see where it says gains. Right there. So when you're going from neutral, no charge, to gaining electrons, you're being reduced. So H. Okay, that's reduction is gaining. Oil rig. Down for these one are litmus papers. Okay, if red litmus paper stays red. So if at the end it's red, I know it's going to be an acid. Or, because it didn't change, it could be neutral. So this one says substance which dissociates partially, that's not what we're looking at, indicates that the substance could be acidic or neutral. There we go, F. Blue litmus paper turns red. Okay, so that's acid for sure, because acids are always red, but it changed, so I know it's not neutral. So I know that one has to just be an acid. Red litmus paper turns blue. Big, bitter blue base. Okay, so I know it's a base, and it changed color, so it's not neutral. So D. Push pause if you need it. Otherwise, take a look at the last couple on your own. All right. Looking down here with you. Okay. This one asks me which one is the most basic. Big, bitter, blue base. So the bigger the pH, the more basic it is, which means 12 is the most basic. 7 is neutral. 4 is a little bit acidic. 1 is very acidic. Solution has concentration of H plus of 1 times 10 to the negative 11th. What is the pH? So our pH is the exponent, but always positive. So I wouldn't say negative 11. I would say positive 11, which means it's basic. What is the pH of 1 times 10 to the negative 6th acid concentration? So I would grab a negative 6, but make it positive 6. That means it's an acid, because it's less than 7. Okay. Down at the bottom, okay, for our extra credits, if you go ahead and write this down at the bottom of page 4, just this side, okay, I'll get 2 points extra credit. That's showing neutral in the middle, 7. Big is basic towards 14, and the closer to 0 you are, the more acidic you are. Okay, and then I drew this just to kind of show you, if you are neutral right in the middle at pH of 7, that means you have H and OH, which is water. Okay, as you move away from 7, you're getting more and more acidic, which means you're having more acid. You can also say you're having less base. As you move towards 14, you're more basic. You're also less acidic. Okay. So when we're labeling them as acidic, basic, or neutral, pH of 7, that's right in the middle. Milk of 6.6, that's just a little bit over here, just a teeny tiny bit acidic. Acid rain with a pH of 4.4, now we're talking like over here. That's acidic. Where OH and H plus ions are equal. That's right there. They're going to react to make water, so neutral. And that's going to happen when you mix acids and bases as well. If I mix a 14 and a 0, they meet in the middle at 7. If I mix a 14 and a 6, they're going to meet in the middle. It's still going to be a base, but it's going to be in the middle of them. Push pause if you need more time. Page 5. We're talking about some safety stuff here on page 5. Okay. So I'm going to let you take a look at this one, number 54. But number 52 says, what are 2 things that you should do if you spill acid on your skin or your eyes? Okay. The first thing you need to do is tell the teacher. Okay, maybe you start screaming, but tell the teacher. And then the best way to neutralize acid that's safe for your body would be with water. So you're going to flush it with water. So in the case of your eyes, you'd use the eye wash station for at least 20 minutes is the rule. I know some of you are dreading this next part. Some of you love the balancing, but we're looking at the balancing. Okay? These are all 3 neutralization reactions because it's an acid plus a base makes water and salt. Okay? So it asks you to draw a circle around the salts, put a box around the acid, and a star by the base. So I'm going to do that. Okay? HClO4 is my acid. I'm going to put a box around this. MgOH, that's the base, and an hydroxide. That's my water, so that means this one is the salts. For this one, beryllium hydroxide, OH, that means it's a base. HCr2O7 is my acid, making water and that thing, which must be ionic, because it's a metal and nonmetals. HF, that's hydrofluoric acid. If it ends in OH, it's a base. There's my water, so there's my salts. Alright. Now the next thing I really want you to do is put back in the parentheses for polyatomics. So that's ClO4. You can keep that together when you balance. Dichromate you can keep together before and after. Okay. So we're able to balance it this way. I'm going to cut the equation in half and write down what I have. I have hydrogen, I have ClO4, which I'm going to keep together. I have magnesium and OH, hydroxide. I'm going to keep those together. Over on this side, I don't see my hydroxide. So this is going to be twice, if 5 times easier, okay, if you remember this trick. So H2O is the same thing as HOH. So instead of doing this, I'm going to scribble this out and make it HOH. It's still water. It's still H2O, but now I don't have to balance hydrogen weird. Okay, so I'm going to say I have H, I have ClO4, I have magnesium, and I have OH. Alright, that's kind of a weird trick, but it is so helpful. And then we count how many we have. On this side I have 1 hydrogen, 1 chlorate, 1 magnesium, and 2 hydroxides. On this side I have 1 hydrogen, because the other hydrogen is part of OH, so I don't count it by itself. I have 2 ClO4s, 1 magnesium, and 1 hydroxide. Okay, let's just figuring out where we're starting. So my hydrogens are already balanced, my chlorates are not. So I go to the smaller side and I make it match. So I would say 1 times something equals 2. Well, 1 times 2 equals 2. So I put this number in front of chlorate. That gives me 2 chlorates. It also gives me 2 hydrogens. So I need to make sure I say, oh yeah, that did my hydrogens. And whoopsies, that unbalanced my hydrogen. So now I need to come to this side, say 1 times something equals 2. 1 times 2 equals 2. So I put that number here. So 2 hydrogens on each side. But that also gives me 2 hydroxides. Okay, 2 hydrogens on each side, 2 chlorates, 1 magnesium, 2 hydroxides. Ta-da! We're done. So I don't put anything in these blanks, or you can put the 1 there. So if the ratio of coefficients, if you remember that, you would say 2 to 1 to 1 to 2. The big numbers out front, the coefficients. Okay, looking at number 56. I'm going to cut it in half. I've got beryllium, hydroxide, hydrogen, and dichromate, Cr2O7. Okay, over here I've got beryllium. My hydroxide is hiding, so I'm going to say, oh yeah, let's take it back out. H2O is an acid, H, plus a base, OH. So there's my hydroxide. I do have hydrogen, and I do have dichromates. Okay. I have 1 beryllium and 2 hydroxides. I have 2 hydrogens and 1 dichromate. 1 beryllium, 1 of these, and 1 of those. Okay. So my BEs are balanced, my OHs aren't. So I go to the smaller side and make it match the bigger side. 1 times 2 equals 2. That gives me 2 hydroxides. It also gives me 2 hydrogens. It's a package deal. So 1s are balanced, 2s are balanced there. Ooh, that fixes my hydrogens, 2 hydrogens, and 1 dichromate. So that's the only change I need to make. That's it. 1 to 1 to 1 to 2. Balancing. Okay, do number 57 on your own, but remember to pull your water apart into the ions, like that. Good luck. Alright, we talked a little bit about oil rig, oxidation and reduction. So what does oil rig stand for? It stands for oxidation is losing electrons, and reduction is gaining electrons. Okay? I always taught my students metals are messy. So metals are messy. Metals are messy, they lose their electrons. They like to be oxidized. So usually metals will be oxidized. Reduction is gaining. It's your nonmetals that tend to gain electrons to be more like the noble gases. So this one will gain 1 electron. Gains 2, gains 3, gains 4. So all of my nonmetals tend to gain electrons, which means they tend to be reduced. So I'm just going to put NM for nonmetals. And that will help me take a look at these other ones. So always when you have pure calcium and pure fluorine, so it's just one element by itself, they are neutral. They have no charge. And after they react, they transfer electrons. It's an ionic reaction. My messy metal calcium will lose electrons to make a +2 charge. Fluorine needs 1 more negative. So it will get 1 more negative. So it asks me which one is oxidized. OIL. Which one will lose electrons? That's the messy metal, calcium. The electrons don't lose themselves. Calcium fluoride is being made. It's being synthesized, but it's not being either. Fluorine is gaining electrons, so that would be reduced. Right? Try 59 on your own. When an atom is reduced, electrons are oil rig, gained. They're not shared, that's covalent. They're not lost, and electrons are not created. Alright, so oil rig is going to be your best bet. Okay, the last thing, we're going to look back here. Okay, I'm not going to talk much about this. I'm going to let you finish filling in the blanks. Okay, I left 1, 2, 3, 4 of them. So use what's there and finish the rest, and then the last 2 points of extra credit. This is your last unit for chemistry. Okay, next week we start studying for our finals. Good job, y'all.